Yep, looks good.
Okay, great. Well, thank you so much for having me today. I'm so excited to get an opportunity to present in the TigerStream Stormwater webinar series. As Matt mentioned, my name is Jaime Schussler, and I am now an assistant professor at Oklahoma State University in the School of Civil and Environmental Engineering. But before I was a cowboy, I was a tiger. And I graduated from Auburn University and I was a PhD student at the Stormwater Research Facility. And I'll be talking about some of that work today. That work is titled Building Better Basins for Linear Projects. And this was based off of an Iowa DOT design. But I want to give you just a taste of who I am and why I care so much about our water resources. I always try to encourage my students to share their water story. And for me, I knew that I always wanted to go in to do something to protect our natural resources and especially our water resources. And why? It's simply because I really love and appreciate my time in and around the water. You can see my husband and I are big fisher people. He's more of a fisherman. I'm more of read a book on the boat type person, but we really enjoy and find our peace around the water. And if we didn't love it, our golden retriever sure does. Even when we try to keep him out, it seems like an impossible feat. He'll beat us to the water most days. And now I have two small nieces who are also little water bugs. And for me, I want to do my part and protect our water resources and make sure that they are fishable, swimmable, and all of the great things. Another thing I try to encourage my students to do is become familiar with their watershed. For me, I am from the lower Guyandotte River watershed in West Virginia. I grew up in Milton, West Virginia. But my education has taken me around the country and even around the world. And through all of this, I've just learned that water is something that really connects people. So after graduation, after high school graduation, I decided that I was going to pursue civil engineering and really try to focus in this water area. And why is that? Well, when I was a senior in high school, we had the Elk River chemical spill, and we were without water, without domestic water for 2 weeks. We had a lot of bottled water around us. We were very fortunate and lucky in that way. But I saw how much of life was disrupted by these sorts of events. And so I said, okay, well, I'm going to go study civil and environmental engineering, and I'm going to figure out what I can do to help and prevent these sorts of events from happening in the future. Well, it didn't go exactly like that. When I was a junior, I got an opportunity to study abroad and exchange for 1 semester in the north of France at an agricultural school. So I went from my land grant school in West Virginia to an agricultural school in France, where I participated in their soil and water management program. I was one of 6 students. I was the only American student, and this really exposed me to how other people around the world see water, view water, manage water. And this really inspired me to continue pursuing this education. I knew I wasn't done yet once I participated in this program. This program was my first exposure to research. We got to participate with PhD students collecting water samples to look at how the European Water Framework Directive was going. And so when I came back for my senior year, I thought, well, I'm going to want to go to grad school and I'm going to want to keep doing work like this. And that's where I started working with Dr. Perez. At the time, we were out at Iowa State, and that's where we formed this connection to the Iowa DOT. And we'll be talking about some of the research we did with them today. Just after I finished my master's, Dr. Perez had moved back down to Auburn to expand and operate the stormwater research facility. And so I was just so excited to go as a PhD student and be working at the facility that I had learned so much about and read all the great research coming out of there. And so we continued work with the Iowa DOT, even though we were about 15 hours away in Alabama. Following that experience, I got to go to Australia, again, just to look at how they were using sediment basins, how different water management strategies were working, and that primed me to then take my position at Oklahoma State University. At Oklahoma State University, I run the Schussler Stormwater Lab. My lab aims to find implementable solutions to manage increased stormwater runoff and sediment loads from construction, urban, and agricultural sites. So we've expanded just a little bit on our construction side of things. Why? Because, well, that's what the need was when I moved out here, was looking at stormwater runoff from all of these different land uses. And I just want to credit my students. Here's some photos of them doing their field work. We do a lot of field work here. And so I always appreciate their willingness to get out and get their hands dirty. So just a couple pictures from the different projects we have going on. In addition to some of the things we do on the research side, I'm very passionate about outreach and education. I love participating in things like these webinars, but we try to engage students at all ages. So we have the Gals in Green Infrastructure outreach group that targets students K through 12, a water research mentorship program that gets those students from high school into college. And I just want to spread the word about all the possibilities and things that they could be doing in the water research space. And then like Auburn, I saw how impactful the training events could be, how the professional development and the learning goes when you get to have hands-on training events with different stormwater practices. So if you are situated a little bit closer to Oklahoma, getting to Auburn is challenging. In October, we do a construction contractor compliance conference where we demo a lot of different erosion and sediment control and stormwater practices. And this is at a USDA facility local to Stillwater. We've got a lot of great partners with ODOT, the ODEQ, the Turnpike Authority, and the Association of General Contractors. So this is just a flavor for who I am. But today I get to relive my glory days of being a PhD student at Auburn working at the Stormwater Research Facility, which I look back on so fondly and was such a great time of my life. I got to do in my final year of my PhD, I was on the Ginning podcast out of Auburn, and they titled this Making It Rain. And so this is what I say is my claim to fame, is I have a, I guess, podcast episode on Spotify. And I love this little episode description by the marketing team. But the biggest thing that I want to pull from that is today we are going to be talking about the world's largest slip and slide, or whatever. And this is what the marketing team had called my sediment basin, which is what we'll spend the rest of today's webinar talking about. So if nothing else, we can get a giggle out of this world's largest slip and slide. So why are we here? Well, in the United States, we have more than half of our waters that are impaired. We've got more than 50% of our rivers and streams that are impaired, and almost 3/4 of our impoundments, or lakes, ponds, and reservoirs that are impaired, meaning they are not fishable, swimmable, etc. And stormwater is one of the only pollutant sources that is actually getting worse. We have a change. We see a big change in precipitation happening. We are seeing more and more extreme one-day precipitation events. And so this is generating more stormwater runoff than previously. And there's a lot of different sources, including industrial stormwater, agricultural stormwater, urban stormwater, and construction stormwater. And construction stormwater is where we'll be spending our time today, or where these sediment basins and building better sediment basins might fit. Construction activities often drive and accelerate erosion and sedimentation processes. So construction exposes a lot of the soil. We no longer have that natural vegetation and protection. And so now we have all of this exposed soil to these increasing rainfall events. And as a result, we see more erosion, we see more polluted discharge. In fact, erosion rates in construction are 1,000 to 2,000 times that of natural areas. And the US EPA identifies sediment along with nutrients, heavy metals, and these things normally sorb or attach to the sediment as some of the most widespread pollutants that are affecting our water resources or our surface waters. So essentially that sediment is acting as a vessel for a lot of other water pollutants. And the sediment-laden discharge has downstream effects. This is a picture taken from a construction site that we were monitoring. And as you can see, this is a private farm owner's pond, likely used maybe for recreation, maybe for irrigation, maybe for watering livestock. But we can see that there are protection measures coming in here. We see maybe a coir mat down. We see some wattles, some rock check dams. But if we look into the inflow into this pond, we see just how much construction can impact these areas. We see this milky brown color, which is just a sign of that sediment-laden discharge. And we've got some check dams in trying to settle that out before it reaches the pond. And these practice, we see maybe they're doing some work here now, but throughout the course of this project, the pond had to be dredged out 3 times. So you can imagine that farm owner's not super happy, water quality is not great, and it's expensive. We don't want to have to do that. So what can we do better on sites to better manage this sediment-laden discharge? Some of the effects that we see is this increased turbidity or this muddiness or milkiness in the water. And then we get increased sedimentation, and this can really affect our aquatic habitats. We also then start to take up these capacities that are normally there to either convey or detain water, but we're taking up storage space now with sediment and making that space not available for water. Of course, nobody wants to see this happening to their pond, so there's poor public perception. We're going to have to treat the water. We're going to have to dredge ponds out. And then, of course, we're washing away a lot of that upper layers of the soil. And I think we all know soil's not being created as fast as we're losing it. So there's a lot of different effects here. And if we could better manage our sites, maybe we could mitigate some of these effects. In 1995, the estimated cost of soil erosion in the US was $45 billion to manage on and off-site effects. Now, I know what inflation is looking like in our house these days. Ooh, having some jumping around. Let's see. Jump right back in. So this $45 billion was last estimated in 1995. So we can only imagine what that looks like 30 years later in 2025. So we've got to be doing better on our sites to try to keep some of this down. Now, what are we doing about it? Well, the EPA does have the National Pollutant Discharge Elimination System, which is authorized to a lot of our states to oversee within their particular state. But we're focusing on this construction general permit or the state versions of this. Now, the construction general permit does require notice of intent on sites greater than 1 acre of disturbance, and it requires a stormwater pollution prevention plan for all construction activities covered in the permit. This includes the design, installation, and maintenance of erosion and sediment control practices. We have to have a qualified inspector to go through and look at these practices and verify compliance with the permit, including regular documentation, updates to any of the erosion and sediment control practices to try to mitigate some of these effects. The construction general permit is at the federal level. The states have to comply with the minimum requirements. However, they may be more stringent. So it's important to comply with state, tribal, territory, or locally specific requirements as well. Now, this is a linear construction site, and linear construction sites are particularly challenging. Why? Well, there are a lot of discharge points on linear construction sites, especially these DOT sites that are spanning miles and miles and miles, and there's really little area to manage. So we have small right-of-way. We've got to be looking at what we can do on our shoulders and within our medians. And so there are particular challenges faced with linear construction sites. And today we're going to be talking about a sediment basin design that might be able to be more easily implemented on some of these sites. Now, it's important to note that regulations, resources, and designs do vary from state to state. What we'll be talking about today is a sediment basin design that was taken from the Iowa DOT and modified to improve performance. Now, there is a divide between these different state guidances. The designs differ. We might have different terminology. Sometimes the guidance can be great, but if we don't have the proper installation and maintenance, then we can't expect our erosion and sediment control practices to perform. And a lot of times we've been using these for years, these practices as rules of thumb or checking the box to comply with some of our regulations, some of our requirements, and using these standard practices. But these standard practices may lack performance data or field testing. And so that's one of the things that the Auburn Stormwater Research Facility tries to address. We'll be talking about how we did this with a temporary sediment basin. But first, let's all get on the same page about what constitutes a temporary sediment basin. Well, this is a temporary sediment control practice that has an inflow structure, a settling pond, a dewatering system, and an auxiliary spillway. Now, the Iowa sediment basin design looks a little bit different. They have this channel with an earthen berm constructed across it. Now, it's important to note this channel is a drainage channel on site. It is not a live stream, and this practice would not be able to be used across a live stream. So it is within a drainage channel on the site. So we have a drainage channel. We have this constructed earthen berm that's 4 feet tall. We have a riser pipe installed through it with these perforations. And then we've got a 12-inch excavation just upstream of that berm, and we can see from the detail that that material is used to then construct the earthen berm. Over top the berm, we do have an erosion stone to protect if we exceed the capacity of that riser pipe, and then have auxiliary flow over at the top. This is what one of those designs looked like newly installed. We can see there's not a lot of stabilization around it. We've got that perforated riser pipe sticking out, and we see this area for the auxiliary spillway with this erosion stone that should be slightly lower than the top of that dam, just to ensure that flow is going over it. Now, if you've been joining these webinars, it might not be a surprise to you that with the lack of stabilization, we start to see some erosion. And hint, if we look on the left side of the screen or the back side of that dam, we see a lot of that erosion start to happen. We see our riser pipe turned over on its side, so we don't have water going through the designated spillway. And it looks like even that overflow is not going over our stabilized erosion stone. Rather, it's flowing over that berm and eroding the backside. And over time, when we're tracking this, this is what it looks like. As we can see that the auxiliary spillway was likely not at a lower elevation than that earthen berm. And so we have major erosion, which is contributing to an even higher sediment load at discharge. Now, we monitored these basins for some time. This is a picture I always enjoy sharing. One day I stepped just a little too far in this sediment basin that had been capturing sediment, hadn't been maintained for some time. And what do you know, I got stuck and had to be rescued. So I've really tried to sink my teeth, my efforts into understanding how these sediment basins work. And so we monitored these basins over several months, and we looked at two different configurations. The first was a single basin. Over the time of monitoring, we experienced about 3 inches of rainfall. And what we were seeing at the discharge of the sediment basin is actually that the turbidity, or that clarity of water, the turbidity was higher, meaning that the water quality was worse leaving the basin than what we were monitoring at the inflow of that basin. We then saw just across that there was a basin in series. We were thinking that that first basin would act as an area to capture rapidly settable solids, and then it would move into the second basin for polishing. What we were seeing was that there was a reduction in turbidity in that first basin, but maybe not quite as much as we would have liked to see. While we were having about 200 NTU removed, our inflow stormwater was in the tens of thousands of NTU. And then it moved into the second basin, and we were having some reduction. And so we start to see some principles that we're working here, that this area, this first basin moving into the second basin, maybe we were capturing some rapidly settable solids, and then moving on into polishing. However, when we compared the very first point to the last discharge point, we weren't seeing that great of a difference. However, we saw a lot of benefits that could come from an in-channel sediment basin design. For example, it uses existing conveyance infrastructure. It increases the length to width ratio of the flow path, which we'll dig into just a little bit more. We are able to really work this right of way, so we don't need more space on the side of our projects. We can use the right of way that we have. We can use this shoulder area, these drainage channel areas, to implement a sediment basin. And overall, we think this would reduce the cost. So we wanted to see what we could do to improve. And so we started working toward this evaluation of sediment basin performance using large-scale testing to put in different structural treatments to see what we could do to improve the performance. The project evaluated the performance of the standard basin along with several modified designs at the Auburn University Stormwater Research Facility. The first objective was to develop a large-scale testing procedure and an apparatus that mimicked the scale and the hydrological behavior of the field-installed basins that we had been monitoring previously in Iowa. We wanted to understand the sediment capture and turbidity reduction of the Iowa DOT standard sediment basin design, as well as the performance potential improvements that were provided by the treatments we introduced into this basin. And finally, we wanted to develop practical and cost-effective design and construction recommendations for Iowa DOT sediment implementation and see how it could be applied elsewhere. Now, this project was one of the first projects in the expansion area at the Auburn University Stormwater Research Facility. Now, the mission of the Stormwater Research Facility is to create environmental stewards within the construction industry by developing improved erosion and sediment control stormwater technologies and practices, and overall advance the body of knowledge through research, development, product evaluation, and testing. So when we started talking about how we could improve the Iowa DOT sediment basin, we started looking back to previous research that had been done and looking at sediment basin design principles. For example, there was a minimum sizing criteria of sediment basins that provided 3,600 cubic feet of storage volume per drainage acre that contributed to these practices. And this was the sizing criteria that the Iowa DOT was using. Alternatively, some states will use the 2-year 24-hour event. However, in Iowa, we were still using the 3,600 cubic foot per acre. The maximum drainage area to a sediment basin recommended was 10 acres. And we wanted to have a minimum basin length to width ratio of 2 to 1, so at least 2 to 1. And this is one area where we saw that maybe our in-channel sediment basin design could really shine. And then wanting to dewater from the surface in 2 to 5 days, we know that the interpretation of this language can be quite different. Maybe some people are using riser pipes, others are using skimmers, and so we wanted to compare that ourselves to see what kind of performance we could get. And then there always needs to be an auxiliary or emergency spillway to accommodate larger events in the case that our primary outlet or dewatering structure the capacity is exceeded. And so wanting to make sure that we have an effective auxiliary spillway, one that's not going to wash out and erode. Other structural interventions that we tried was putting in a forebay and also looking at baffles to dissipate the flow energy and spread flow across the entire basin. And so really just remembering what some of these design principles are that have been backed by previous research and seeing if they could still provide performance improvement in the in-channel design. And so we came up with this experimental testing regimen. We can see that we started with an unlined sediment basin, the standard design, very similar to what I was showing in those earlier pictures. And then we moved into lining the basin with a geotextile just to try to provide some stabilization and mitigate any erosion and additional sediment contributions from the channel and the basin itself. Now you can see that's indicated by these blue lines on the right side of the boxes that we were using Alabama soil. Maybe you're asking, well, why do we have these two different colors, Alabama and Iowa soil? One of my favorite parts of this project was that we actually had 5 tractor trailer truckloads of Iowa soil delivered to us directly from the construction site that we had been monitoring in person, trying to make sure that we had as realistic conditions as possible at the testing facility. So this first comparison was really just to look at the difference between lining the basin. And then we moved into that same test, but using Iowa soils so that we could make comparisons between the two soil types before we started adding these other structural practices, including using a surface skimmer, so replacing that riser pipe with a surface skimmer, introducing those porous flow baffles across the basin. So these coir baffles to dissipate the flow, spread flow across the entire width of the basin. And then also introduce a forebay within the channel to try to capture those rapidly settable solids like sands. Then we would take a look at all of these structural practices and then decide what is our most feasible and effective installation that we could use. And that's what this MFEI stands for is, well, should we throw it all at it? Is that feasible? Are each of these practices effective? And then going from just looking at it structural practices to now adding chemical treatment or flocculant in the basin. In total, there were 48 tests. We would introduce flow and sediment into the basin for 30 minutes. That would bring the basin to its capacity. We'd allow it to dewater for 4.5 hours before we introduced a second round of flow and sediment introduction. And this was to simulate another rainstorm or another event coming in. We then let the basin dewater for 48 hours before we went through this all again, a second and a third time. So in total, 48 tests. The basin installed at the Auburn University Stormwater Research Facility is 200 feet long. It had a 10-foot bottom, 3-to-1 side slopes on one side, 3.5-to-1 side slopes on the other, 5 foot deep at its deepest point, and 42.5 feet wide at its widest point. If we look at the bottom width to the length, we have a 20-to-1 ratio. So as you can see, we've greatly increased that length to width ratio. And so we wanted to see, does this provide increased performance? This is what the basin looked like during construction. We started with that riser pipe, as you can see, soil exposed, similar to what we were seeing from those field pictures. On the right-hand side, we see that riser pipe sticking out, and then our auxiliary stone spillway. We took a base case, a LiDAR scan of this to understand how our build was. We had about a 3% slope in there. And then we started to do our calculations for what our flow and sediment introduction needed to be. Again, this was an Iowa project being conducted in Alabama. So we did some hydrological analysis to come up with our flow rate. Our flow rate ended up being 1.7 cubic feet per second based on a 2-year, 24-hour precipitation event. And then we also had our soil introduction that ended up being 62.7 pounds per minute. In total, we were introducing almost 2,000 pounds of sediment into this basin. That was done based on the mussel soil loss equation using a curve number for newly graded and developing areas, state average of 91.64. As I mentioned, we had Iowa soil delivered. Now, when it delivered, it was a lot of different colors. We didn't know if it was taken from different spots on the site or what exactly happened. So we spent quite a bit of time drying this soil, crushing this soil, mixing it together, and homogenizing it for the rest of our testing. Now, this is what the sediment basin setup looked like aerially. We can see this big black basin, or the world's largest slip and slide, as we lovingly call it, in the middle of the screen. On the far left side, we had our sediment and flow introduction apparatus. And then we went ahead and split our basin into 4 bays. We delineated 4 bays. While the coir flow baffles would really be the delineators between these bays, we wanted to make sure that we had this throughout testing so that we could do reasonable comparisons between the treatments. And so you can see here the even bays that were considered Bay 1, Bay 2, Bay 3, and Bay 4. Far right side, we see the dewatering mechanism, which is just that little white dot in this picture. And then so we start with our liner, and we can see that we just have a little bit of sedimentation. It comes up to just about here. Then we move into having this skimmer. And so the skimmer comes in and we really start to see this increase in sedimentation. It's further up the sides of the basin and further up the channel as well. And why is this? Well, that skimmer allows for more water to impound, more water to back up in the channel. And so we see these sedimentation patterns start to happen. With baffles, our first flow baffle, we see quite a bit of this heavy sedimentation that's happening in the channel. And that's similar to what we are also seeing with our forebay. Now, when we compare the sedimentation retained by weight, we can look at the Alabama lined. We had just about 60% total retention. When we started to move into testing with the Iowa soils, this was slightly increased, but really we started to see our substantial difference with these structural changes, with the skimmer retaining 88% of the sediment introduced, then having 84% retained when baffles were introduced, and with our forebay now getting 89% sediment retention. And so these colors are indicating how much sediment was retained in Bay 1 in the red, in Bay 2 in the yellow, Bay 3 with the blue, Bay 4 in the green. The gray was the sediment yield, or the sediment leaving the basin. And we can see with the skimmer and the forebay, there's this light blue color that is introduced. And why is that? That is because we now have water impounding back up the channel and dropping sediment out in the inflow channel. When we started talking with the project sponsor about what would be feasible and effective, they thought, well, hey, we can put the liner down, we can swap out the riser for a skimmer, and the forebay was just created with a small rock check dam covered. And so these all seem like reasonable modifications to make. And so that's what we moved forward with as our most feasible and effective. In addition to looking at these practices, we also introduced flocculant. Now, flocculant is a chemical agent. It would be applied upstream of the sediment basin, and this helps to bind fine particles to create larger particles to promote gravitational settling. So we've now taken these really small clays and silts, they bind together to create a much larger flock that's heavier and larger and can drop out of suspension more rapidly. So our MFEI looked something like this. We had the geotextile liner, we had the rock check dam that created the forebay, and then we had that skimmer dewatering mechanism at the very end. When we introduced flocculant, we used these flocculant block type products that were put right at the end of sediment and inflow introduction. This allowed all of the water to pass over the flocculant and provide ample time for mixing. Now, this created the contact time between the sediment-laden water and the flocculant, and it was able to mix to really integrate that in. Then there was some settling within the forebay area and more within the end of the basin. The flocculant application was selected based on match tests that were developed in another research project at the testing facility. The matching considered effluent color, the settling velocity, flocculant size, and formation. In total, 14 flocculant products were evaluated with the soil. And then we identified a polyacrylamide product that was available in block form. Again, talking with the sponsors, the block form was the most desirable just because of perceived ease of installation there. We monitored the water quality in the forebay, and we also looked at residual concentrations of flocculant at discharge following the methods also developed at the testing facility. Now, the picture on the left is showing what the sedimentation was without flocculant. You can use some of these cinder blocks as gauges to see where the settling was occurring without flocculant. So closer to the forebay, we had these larger cinder blocks. If we pay attention to these two cinder blocks, particularly on the right, we can compare this then to the right-hand side of our screen. We see that not only does that settling back further up the channel, but it's also much deeper. So we have quite a bit more sedimentation that's happening when that flocculant is introduced. Now, if we compare that, excuse my scribbles, I guess I shouldn't have done that. When we compare this from a sediment retention standpoint, with the most feasible and effective installation, we had 96% of sediment retained. When flocculant was introduced, we were able to get up to 98% of sediment retained. And you're saying, well, Jamie, this is really just 2% more. But again, we were measuring the sediment retention by weight. So taking all of the sediment out of the basin and weighing it. When we think about those really fine particles like clays and silts, that 2% is actually quite a bit of taking out those small particles that are then going to cause that turbidity or stay suspended in the water for long periods of time. So we add these two installations in, and basically what we can look at is when we compare this lined to the most feasible and effective installation, we see a 20% increase in sediment retention by weight. When we introduce that flocculant, we actually have a 22% increase in sediment capture. Now, this is a lot of sediment retained within the basin, and what does it look like for turbidity? Well, where I would really like you to focus your eyes are on these bottom two lines of this pink and these green lines. The pink indicating the most feasible and effective installation, the green indicating that same installation but with flocculant. What we see when we introduce flocculant is that we can drastically drop turbidity. In fact, we can achieve around 100 NTU within about 30 minutes of settling time. Now, when we're dewatering much cleaner water over the dewatering period. Now, you'll see with the skimmer, that is the red treatment. The skimmer was also used in the MFEI installations. We're seeing dewatering over a longer period of time because that skimmer is able to draw down water to the bottom of the basin. However, when we use the riser pipe, the basin can only dewater to the lowest perforation. And so what's happening is we're actually holding water in that basin. We're holding more water in that basin. And it's unable to leave if we don't have lower perforations. And so the skimmer is actually able to draw the water down and free up more storage in the basin. Additionally, we're discharging clearer water or less turbid water. We compared as well the grain size that was captured when flocculant was and was not applied. So we were looking essentially at the size of the soil particles that were captured using the most feasible and effective installation. You can see that those installations with the solid lines. So the red indicating this was the grain size captured in the forebay, the blue being the grain size captured in the third bay, and the yellow captured in the fourth bay. So the solid lines were the most feasible and effective structural installations. And the broken lines or the dotted lines are when flocculant was applied. What you can see is this general shift to the left or to a smaller grain size. And so we were able, when flocculant was applied, we were able to capture much finer soil particles. In fact, the D50 was decreased by about 51% when flocculant was applied. So we were able to capture soil particles half of the size when flocculant was used. Now, our main takeaways was that flocculant improved turbidity reduction by about 42%. It captured particles 51% smaller. When flocculant's used, we can increase the settling rate, And this provides a potential to maybe even decrease detention time. If we go back to that turbidity chart, we see that we nearly plateau. We get around 100 NTU even within a few hours of settling. Now, we might get some smaller reductions over time, but we have to trade off things here. Can we create smaller basins? Can we dewater more quickly, freeing up more storage capacity? So the flocculant does pose a lot of interesting questions. Additionally, if turbidity limits are imposed, flocculant could be a really great way to achieve some of these turbidity limits. With structural practices alone, it's really challenging to capture those clay and silt particles. Now, there is concern about how much flocculant are we discharging from these basins. Well, we did monitor residual concentrations. We saw the concentrations averaged at about 5 to 6 milligrams per liter. And when we compare this with safety data sheets of flocculant, we really didn't see a lot of risks that were associated with these concentrations. Now, quickly, just to put this design into practice, we did create an in-channel sediment basin design tool that's based in Excel. It allows you to input your channel configuration, your earthen berm or dam spillway configuration, and select between 3 different dewatering systems, including a skimmer, a riser pipe, and a rock weir. If a skimmer is used, it does let you select the desired dewatering time. And using that, it can even recommend a skimmer size to you. Now, this is based on one skimmer manufacturer. We know there's different things on the market. In this case, we were using a fair cloth skimmer, and so that was what was built into our design tool. If you had the soil gradation, you could input that. And it would come out and tell you what the storage was in your basin, what your skimmer size was, and based on these different parameters, if you elected to input them, it would predict if you were going to have 80% or higher of sedimentation that occurred within the basin. If anything less than 80% was predicted, then it did recommend the application of flocculant. So there's a lot of things that we could go into on this tool, but for the sake of time, I am going to stop here just to make sure that we have time for questions. The design tool does give you a channel cross-section, a stage storage curve, and also a stage discharge curve based on your selected dewatering system. I'd be happy to spend more time with this. This is available through the Auburn University Stormwater Research Facilities website. But with that, I am happy to take any questions that you might have.
Thanks, Jamie. As she said, we're going to open the panel up for questions. So Q&A, let's see, Jeanette Wolf, how do I allow you to talk?
I think I can see it in the chat. Yeah, and so is the design tool spreadsheet publicly available? Yes, when we completed that, it was hosted on the Auburn University Stormwater Research Facilities website. I think Dr. Perez could confirm if it is still on there or not. However, if you struggle to find it at all, just shoot me an email and I'd be happy to share that with you. Is the liner for sediment basin a requirement? If so, is the liner a concern during maintenance? That's a really great question. A liner is not a requirement, but what we were seeing in the field monitoring was that the basin itself, the channel, the side slopes, there was a lot of erosion happening. Now, this might be more or less pronounced depending on your soil type. Maybe you've achieved stabilization with vegetation. We were really struggling to get vegetation to establish within the channel, within the basin. And so we were seeing a lot of erosion happening in the channel. The sides were getting saturated. We saw some sloughing. So we were introducing an increased sediment load. So that's why we elected to put down a liner. So we just used a geotextile liner to provide that stabilization and make sure that we weren't increasing the sediment load to the basin. It was just what was running off and coming in. Now, I'll tell you that we had to clean out this basin many times throughout the process of testing. And we were able to use a mini excavator to dredge out the basin. We had to be careful. I mean, we didn't want to break the geotextile, but we could get down within, an inch or two and then just finish it out. For us, we wanted to get every bit out just because we were measuring and quantifying. However, you could get a lot of the material out in practice with just some small equipment, like an excavator, and maybe it's okay to leave that last, 1 inch or so of sediment at the bottom. So it is not a requirement. However, we do see a lot of benefits, and with some clear communication and expectations, we don't expect it to be a big problem with maintenance. Now, that is why we elected to not use the baffles, is because we did think it was going to be really challenging to maintain around those. Was the sediment basin cleaned out after each test? And was this a challenge or excessive work? Yes. The sediment basin was cleaned out in between each, I guess, treatment. So, for example, we ran the tests for, say, all of the skimmer tests, and then the sediment was cleaned out. And like I said, it was done very meticulously. It was dredged out and it was put into containers to measure. And so, yes, it was cleaned out in between each treatment. It was a huge challenge, and it took about 5 people to do so. Now, again, I think if you were doing this in practice, you could use some equipment to dredge it out. You wouldn't necessarily care as much about quantifying the weight of the sediment. Okay, next question. Did you monitor laminar flow in the different bays? And could this explain why the particle size retained in Bay 3 was smaller than before outlet velocities? That's a really, really great question. We actually were not monitoring flow in the different bays, but I think you make a really great point, Clay. The outlet velocity or creating some mixing right there at the outlet, I think, yes, that's possible that we could be suspending particles, and that might be why our particle size was the smallest in Bay 3. How do you get a contracted installer to use the non-woven geotextile liner? That's a really good question too. Non-woven was spec'd out in the Iowa DOT specifications as an acceptable engineering fabric, and so that's what we decided to go with. It was used on other areas of the site, such as under construction exit pads, etc. And so that's what we decided to use in the basin. Again, I don't know that it has to be a non-woven geotextile liner as much as we just want to achieve stabilization in the basin. We did this using a geotextile liner. If you can get vegetation to establish, if you have different mechanisms, different means of stabilizing the basin, maybe with different matting, etc. I think it's more about stabilizing that basin and make sure we're not eroding as much as it is the material. But again, the non-woven geotextile liner was just a spec'd engineering fabric that was used on other practices, and that's why we elected to do so. Okay, how would you determine the P factor to use the Russell calculation given the improvements to the traditional sediment trap? Would a P factor of 0.1 be reasonable? That's a really good question. I haven't really dug into that analysis. don't necessarily want to answer it on the fly without being more informed. So I'll say, Abdi, that I'll look into that, and I'd love to keep in touch on it. What product or material was used to line the basin? Did you do testing with other materials? So we did use a non-woven geotextile liner. We did not test any other materials in this application. But I'd be happy, in that report, it has the exact specifications of the weight of or the density of the material. And then I'd be happy to follow up on that as well. I am remiss right now to try to think of that. So yeah, but I really appreciate the questions. That was really great. And again, I'll put my email in the chat. Thanks, Mike. And Dr. Perez did drop a link to the tool in the chat box. Okay, and did the basin performance decline in subsequent tests? I would say, John, it really depended on the treatment that we were using. In some cases, we did get a little bit of resuspension of soil particles. We ended up, the turbidities that you were seeing were taken, they were an average between the tests. So yeah, it definitely depended on the structural performance that we were looking at. Just because if you do have material in the bottom of the basin, you do get some resuspension. Of course, we'd love to be starting with a clean basin every time. But yeah, we did not perform the maintenance until after. So, and the final report, it does have some more talk about the average and the standard deviations between the 3 tests. Okay, and I am trying, let me see if I can. Matt, I'm struggling to type in the chat. Would you mind dropping my email address in there just in case people want to copy it over?
Yeah, absolutely. How do I SCHUSSLER? And that's at OK State
Yes.
edu.
Yes.
And Jamie, I apologize. I pronounced your last name wrong at the beginning
That's
of this. It's Schussler?
Yeah, my dad always says it's like hustler with an S in front of it, so Schussler.
Well, that's easy to remember. Well, Jamie, thank you very much for taking time today to talk to everybody on this webinar. In the chat, we shared Jamie's email. So if you all have any further questions, please reach out to Jamie. And then this video will be available on our YouTube. So I also shared the YouTube link. And you can follow us on LinkedIn as well. Just type in AU Stormwater on LinkedIn, give us a follow, and we'll be updating. We update it pretty frequently with webinars like this, but thank you all for your time. The PDHs will be automatically sent out, so just keep your eyes on your email, instructions for how to, I guess, collect all that. That'll be sent out in the coming days, but thank you again, Jamie. Thank you everybody else for your time today.
Yeah. Hey, Matt, there looks like there's one more question to link the final report. So if we could hang on just a second, I could get that dropped in the box.
Absolutely. Jamie, are you putting that in the chat box? Are you able to do that?
I don't know why I'm like struggling to type. I think I can type an answer directly to it though. Okay. I'm actually, yeah, I think it might be the setting. I'm getting locked out here. Yeah, I'm not able to type. Mike, is it possible? Can you drop the link to that final report?
Yeah, I'm working on it. I'll get it on there.
Thank you.
All right, I just dropped it in there.
All right. Well, if there's, thank you all. Yeah, I think if there's no further questions, feel free to reach out via email. I really appreciate the questions because it's given me some more things to think about. So much appreciated, Mike, Matt, Auburn Stormwater team. Appreciate you having me.
Thanks, Jamie. All right, everybody, we appreciate you joining, and keep your eyes out for the PDHs.